And I'll just wait a minute for you to answer this question. Okay, so I see that most of you have voted. I will then close the poll. Thank you very much. And this is basically the result of the answers that I received. So are you involved in dynamic engineering of piping systems? Well, basically the answer is 88% of you says yes, and 12% of you says no. Well, of course, I think we can explain this by the fact that you are all interested in this webinar topic. However, I still find it quite interesting because in many cases, many projects that we see as well, engineers are focusing mainly on static stress assessment and not that much on the dynamics of the piping system itself. So this is actually very good since you will see in this presentation that the dynamics are very important and can definitely contribute to the integrity of the system. Okay, so thank you very much again. We will now continue to the webinar. So I want to start with a small classification of two-phase flow-induced vibrations. And this classification is provided by the GSME, the Japan Society of Mechanical Engineers. They published this in 2003, and I think this is a very neat overview. They differentiate between 3 excitation mechanisms and then 3 types of interaction with piping systems. So the first one on the left is momentum fluctuation, and I think this is the main excitation mechanism, and that will also be covered in detail later in this webinar. Because momentum fluctuation, basically the impact load due to changes in density in piping, are definitely a strong cause for fluctuation, for vibrations of the piping. 2 other categories are defined: thermal hydraulic vibration with phase change, and that is basically related to energy transport between the 2 phases, so gas and liquid, or even energy generation. And that is mostly, you can think of boiling, condensation, so any chemical process that might cause, for example, vibration of internals in your system. And finally, bubble-induced vibrations. I think this is rather clear due to the unstable nature of several bubbles in flow, and definitely the differences in sizes. You can have interaction with piping and hence vibrations. Now 3 types of interactions are defined. One is axial flow, and that is in case the flow, the two-phase flow, is on the outside of the piping, so not on the inside, on the outside. An example can be inside heat exchangers. If there is two-phase flow, for example, bubbly flow in the heat exchangers, then the U piping can be excited due to this two-phase flow. And then this one, the axial flow, means that the flow outside of the piping is in the axial direction. Totally on the right, we see cross flow. That is basically a similar process, but then the flow is in the cross direction of the tubes in the heat exchanger. However, I think the main interesting classification is internal flow, so two-phase flow inside a pipe that interacts with the pipe and causes vibration. Now this classification is discussed in detail in a publication done by Miwa et al. Last year in 2015, and he also states internal two-phase flow-induced vibration is significantly important to secure the reliability and integrity of the piping in power or process piping systems. Now for the remainder of this presentation, I will focus on these two classes, so momentum fluctuations inside a pipe. That is also, I think, for which we do most of our related projects, but definitely the ones that will be discussed in this webinar. So the remaining content of this webinar is divided in 4 categories. So general characteristics, which is next. Then I will discuss some engineering approaches, so basically what to do and some practical guidelines. One example case, and then I will finish with some closing comments. So here we see some visualizations of two-phase flow regimes. Basically on the left we see well, several flow regimes, so stratified smooth flow, stratified wavy flow, then elongated bubble flow, slug flow. I think it's always nice to remind you all that the actual slug is this part. So the red section is a gas pocket, but the actual impact force is due to this section. Then we have annular flow, wavy annular flow, dispersed bubble flow as the last. And on the right we see a measure for the gas velocity, so the superficial gas velocity, and on the vertical axis, and we see the superficial liquid velocity on the horizontal axis. So both are a measure for the gas velocity or the liquid velocity. And we see that these two parameters allow you to classify your flow in one of these flow regimes. And these types of images, these types of plots are also used by programs that predict or calculate, depending on your input, which type of flow regimes you can expect. So this is another visualizations of these flow regimes. So on the top we have dispersed bubble flow, and when these small bubbles are grouped together, we can get slug flow depending on the velocities, of course. And again, this is the gas pocket right there, and the actual slug in this case is here. Alright, then there's also a visualization of annular flow, but I think if you want to know more about these types of classifications, I would recommend to check out the books written by Ove Bradland. Ove Bradland is a researcher and a well-known person in the field of flow assurance. And he wrote 2 books which are free for download on the website shown at the bottom right. And these 2 books, I think especially the second one, focuses on multi-phase flow, and a lot of these topics are discussed in detail in this book. Okay, so a little bit more on slug flow. So we define 2 types of slug flow formation. The first is terrain slug formation, and that is basically due to elevation differences in the piping, which cause water to be collected at the low points in these piping configurations. And then as soon as the gas pressure builds up at the upstream side, the liquid column is pushed uphill and pushed through your piping system. And then also always some liquid falls back to the bottom and is collected at the bottom again, and basically the whole process starts over again. Now this is different process than the second one, hydrodynamic slug flow formation. And this type of slug flow formation mainly happens in horizontal lines. So here we have basically a small wave, which is an unstable surface, and due to the gas flow it grows and can fill the entire cross-section of the piping. So now we have an entire cross-section filled, so basically a slug flowing through the horizontal line. Now once we have these slugs, they act on each elbow individually, not only on elbows of course, also on T's or even reducers, and the total force, the total impact force exerted by these slugs can be calculated by the mass flow times the velocity, assuming that the slug covers the entire pipe cross-section, which you could say is conservative. So we find the maximum slug force as the max flow times the velocity, so the density of the fluid times the inner surface of the pipe times the velocity squared. Now this force builds up as the front of the slug enters the elbow. This is basically the rise time as defined in the graph you see. And then as soon as the entire slug is, well, basically the entire elbow is filled by the slug, we have the maximum slug force. And as soon as the back of the slug enters the pipe, the force is reduced, and the force becomes zero again as soon as the end of the pipe exits the elbow, of course. Now what we see is basically that passing slugs result in hammering effects on these elbows. So rather short but high force impacts on elbows, which can definitely cause vibrations if these forces aren't absorbed correctly. Now the difficulty when analyzing this phenomena are the parameters, so the slug velocity, the slug length, and the slug period, because these parameters define the time history in case you want to analyze multiple slugs passing through your system. Typically slugs represent low frequency and high amplitude vibrations, but to obtain these parameters can be quite hard. In some cases we receive it from clients that have done extensive analysis of the flow regime in their system, but often this information is not available in a lot of detail, and estimations have to be made. And when doing this, we have to keep in mind that these parameters influence the reaction of the piping. So we can have forced excitation versus resonance mechanical response. This is visualized here by a small piping section with two elbows and a slug passing in and hitting the first elbow, causing of course a displacement at the elbow and also associated stresses. We have to note that this piping section has a mechanical eigenmode, a resonance mode at 4 Hz. And we see that depending on the value that we choose for the slug length and the passing frequency, that we calculated different elbow displacements. And of course, as soon as the passing frequency becomes closer to the eigenmode of the system, the impact force is amplified, the displacement is amplified, and the system goes into resonance. So these hammering slug forces can lead to critical forced excitation in case you're not close to eigenmodes, or can become amplified in case you have resonance. So choosing these features can be a very important step in your assessment, in your analysis of this phenomena. And often we relate them to maybe the amounts of volume that are available, or clients do extensive calculations on the type of flow regime that they have. But often also, I mean, you just have to be conservative or vary these values and see what you find, and in which cases there is or is not a problem. Alright, next I want to talk about some engineering approaches knowing these backgrounds that I've just discussed. Okay, so how to deal with slugging during the design stage. And I think this holds for not only slugging but also for other two-phase flow regimes. So basically slug flow is quite difficult to predict in the early stage. There are several two-phase flow programs available, and they definitely give some very usable output. But in the end it's always quite hard to see what the actual flow regime is. However, we know that some systems are more likely to be exposed to slugging. For example, in the upstream sector, risers, well lines, flow to separators, of course, and in the downstream sector, crude furnace sections, distillation tower feed lines, and steam lines. And on the right, you see an image that shows a burner, and here we see, well, basically on the bottom, if I'm correct, we see the radiant section, and here the convection box. And what happens here is that crude oil is being heated, and then the heated crude oil is being fed to several fixed back reactors, two of them which are displayed in this image. Now, when analyzing such a system, I think we can estimate that especially this feed line going from the heater towards the reactor, so this feed line right here, is prone to two-phase flow, right? Simply because we have crude oil being heated and then fed into the next step of the refinery process. And this line typically tends to have two-phase flow and also tends to be well, can vibrate. So that will be definitely one of the lines that that I would have a look at during the design stage. So then which actions can we take? Well, first of all, there are some flow charts available. This one is an example from the Energy Institute, and they allow you to take, well, basically a step-by-step approach to estimate the likelihood of failure. I think that's the first assessment, well, some actions I would definitely recommend during the design of such a system would be the removal of low-frequency eigenmodes. So if you remove these frequencies by adding supporting, then these supports will most likely be able to absorb the slug forces. Now, of course, this is not enough. I mean, you can remove the low frequency eigenmodes, but you also have to design the supports that you use for the slug loads. So the allowable forces on these supports, including the clamps and the shoes, all have to be sufficient to absorb these impacts. Avoiding of certain routing, avoidance of slugging regime. Well, of course, if you are able to predict it, then you are also most likely able to avoid it. Maybe by using an orifice or something alike, you can tune the regime to a different. You can tune the flow to a different regime. And well, I think the more advanced step would be to do a detailed mechanical response assessment, but you would have to base them on assumptions instead of measurements. So conservative assumptions, as I just showed you, you'd have to tune the parameters to get conservative results. How to deal with slugging during the operation stage? Well, this is a typical example of a project that we come across. So vibrations or failure even are observed, and the user, the operator, is alarmed by this. So the first thing that is often done is that measurements are taken depending on the outcome of these measurements, a decision is made on whether things have to change or not. Again, flowcharts are available. Again, an example is provided here from the Energy Institute. But the next step, I think, would be to assess measurements. So basically do measurements on these piping systems, and then you have vibration-based limits available as the VDI 3842, which allow you to make an assessment of the severity of these vibrations. What you do is basically you measure the acceleration versus time, and you translate this to the velocity versus frequency. And you then plot this value, so the root mean square velocity, in the diagrams provided by the VDI. And the lines provided in this plot on the left bottom give some indication of the severity of your vibration. However, these lines are often considered as quite conservative. Well, basically, there is no information yet used of the geometry of the system. So I think these have to be conservative and are worst-case scenarios. Different type of vibration-based limits is provided by the Energy Institute. And again, you have a plot available to do some assessments of the vibrations that you have. But in the end, if you want to know well, in detail what the stresses are of your system, you can always do a detailed mechanical response study which you base on measurements. And by doing so, you are able to get a calculation of the stress caused by the vibrations. And you can use this to assess, for example, the risk for fatigue failure in your line. Now, of course, well, the more advanced you do your study, the more time-consuming and costly it will become. So often, and I think this is also represented in the available flowchart, you will start with just doing this flowchart, making the observation, doing the vibration-based limit, and then depending on the outcome of that, decide if a detailed mechanical response study is necessary. Now, what I also want to highlight is when doing these detailed mechanical response analysis during well, operation, of course, measurements are a big part of it because they allow for quite accurate inputs into the calculation. And of course, you always run into several practical issues. Often, well, there's often not that much information available, especially if the systems are a little bit older. But also, when doing these measurements, you really have to have a very close feel for the locations of doing these measurements, the directions in which you want to measure. If scaffolding is provided, if the insulation has to be removed, probably it is a very high operating temperature. So if the sensors and the equipment are all okay for this. This is an example of a measurement that I performed. Very basic measurement, but I think you see that this, if you want to assess vibrations in such systems, that it can be quite a hassle to get this done, and especially if you don't know what mode shapes your system has. So you would definitely have to do some calculations first to see where the mode shapes, the displacements are high, and then do the measurements at these locations. Another thing I want to point out, another practical issue, is the fact that the design of such systems, this is also part of a burner system, that the design of such systems is often tuned for the static situation. So in these very hot operating systems, you have quite some thermal expansion, and the entire supporting is fine-tuned to allow this thermal expansion to happen. And of course that is very good from a static point of view, but it also allows for a lot of vibrations from a dynamic point of view. So here we see 4 horizontal lines in which crude oil flows from a convection box to a radiant section of a burner, and we see that there is definitely sufficient supporting available for weight. You see that this supporting is provided by hangers, which allow for a lot of thermal expansion, of course. But we also see that if we start hammering these lines, if slugging occurs, then there is no real support to absorb any of the impact loads, and the lines can easily start shaking and vibrating. One of the solutions that is used quite often are snubbers. So snubbers allow for slow expansion, so thermal expansion, slow movement, but they damp very sudden movement. In this case, I think it's clear to see that this will not add a lot of fixation to in case of slugging, since the slug will provide forces in the axial directions at these bands and not in the transversal directions. So I'm not sure what the reason was for the installation of this specific snubber, but it will not add much to absorb slug impact loads. And I think this really shows a typical example, a typical engineering issue. So if you are designing for static assessment, if you are designing for a static situation, then you really want to provide flexibility to absorb, to provide flexibility to allow for thermal expansion. However, this is the exact opposite that you would want to do in case you are designing specifically for dynamic features, because if you fix the system, if you fix the piping better, then of course it is less prone to vibrations. So yeah, you'd also always have to find a balance for this. I think you can always find this balance if you, during the static stress assessment and the design, you already take into account what eigenmodes are present in the systems. Most stress assessment software have some modules for this, and they allow you to calculate these eigenmodes. And taking this into account for your static assessment and static solution already helps a great deal regarding the dynamic solutions. Okay, next I want to discuss one example case of a project that I and my colleagues performed. It is regarding a fatigue failure that was observed in a hydrogen cyanide ammonia stripper in the feed line towards this stripper. I will be discussing the system and then how we implemented the slug load and how we performed the detailed mechanical response analysis. So these images provide an overview of the system. Basically the feed line starts at a heat exchanger and then flows towards the stripper. And I think you can see on the image on the right, the zoom, that there are quite some features that we included in a little bit more detail than we would usually do for a static assessment. You see that I've included some steel structures and also some support attachments on the stripper itself. And the reason we did this is because it is very important in such dynamic assessments to properly module the eigenmodes, to properly allow calculation of the eigenmodes. And this asks for a little bit more detailed modeling, where you would, for a static analysis, for example, use a friction coefficient that is conservative. For a dynamic analysis, in case you want to properly model your eigenmodes, you would really have to use a very realistic friction coefficient. And that can either be 0.4 or a little bit less or more, depending on the surfaces of the supportings. But you would also have to properly take into account the flexibility of these supportings and really the flexibility in your entire system. Because if your system does not reflect the proper eigenmodes, then the response of your piping, if you provide measurements from the actual existing system, well, yeah, they do not match. So you basically don't see resonance in case there could be resonance. So these modules really have to be modeled in detail, and it takes some tuning and time to properly do this. In this specific case, there was a fatigue failure located at one of the welds above the elbow, pointed out with the red arrow. Vibrations were measured, and these were compared to the guidelines that I just showed you, the VDI 3842. And from this, it was, well, basically confirmed that these vibrations had to be solved. I think the failure itself says enough. The frequencies of these vibrations were found between 4 and 9 Hertz. So here we have some visualization of the vibration measurements that were done. So the accelerometer provides the acceleration versus time, which can then be transferred to the displacement or the root mean square velocity as a function of frequency. In this case, well, we found several data points which are alarming, and I think this is good because it confirms that these methods really show quite a good image of what is happening, since there was a failure in one of these bands, and maybe these other data points, other locations, and other vibrations could also lead to failures in the near future. So based on all this information, of course, a detailed mechanical response analysis was performed, and the slug details were provided by the client in this specific case. And the slug forces, the slug impact load was found to be around 3 kilonewton. So our assessment approach was to implement several of these slug forces over time on the systems and on the elbows close to the failed elbow. I think you can see on the right all of the arrows, all of the directions of these forces that we have included, so all the impact forces of these slugs passing through the line. And what we found was that resonance modes were indeed being excited near the failure location by these unbalanced forces. So we found one eigenmode at 4.7, one at 6.6 Hertz, and this really matches closely to the field observations, which observed a frequency range of around 6 to 9 Hertz, and also the mode shape that they visualized was quite close to the one that we see. And basically from this calculation, this time history analysis that was performed, the stress amplitude could be obtained for several of the locations, including the failed band. Now the red lines you see here are the stress amplitudes that were calculated. This was done in this case at Caesar 2. And these were compared to the SME section 8 division 2 smooth bar failure curves. Now of course, whenever comparing these two, you always have to take into account a factor of 2 due to the different base stress intensification factors that both methods use. And I think it's clear to see that if you amplify those red lines by a factor of 2, that you are close to, and in some cases over, the endurance limit. And we have to keep in mind that these vibrations, well, they account for a lot of cycles in a relatively short time. So for example, if you find several millions of cycles, if you're cycling at 10 Hertz, that can still definitely become a problem within a realistic time span. So even if your system is normally not operating in the slug flow regime, if you then for some reason operate with slugs for say a week, still, even though it is for this short time period, fatigue problems can arise. Now following from this, the action to take, of course, is to eliminate these low frequency eigenmodes. So restraints were recommended, several locations and several functionalities. I want to recommend, you have to keep in mind that you always have to assess the static stress situation again, and also take into account the maximum loads on these restraints. And in this case, well, the system was in operation, was not taken out of operation due to this failure, and a clamp with a backing was provided on the leading elbow. So we included this weight and evaluated the influence it had on the eigenmodes and on the eigenfrequencies, and if the situation was okay for both with clamp and without clamp, because the clamp could only be removed well, during the first shutdown. That would not happen soon. So just some examples of that, what we found during typical projects. And I think something to emphasize is the type of implementation. So it's quite easy to recommend what supporting has to be included. You know, if you do the analysis properly, you can add these supports and eliminate the eigenmodes. But we have to keep in mind that in case of a failure and in case of these situations, the supporting is often added during operation. So also if you know, customers see a vibration and they want to act on it and eliminate them, then they probably want to do it while the system is still in operation. So then the question becomes how to install a support, for example a guide, on a vibrating line. That is always a big issue. So we've had a lot of discussions in the past about fixing the lines, the steel cables, or all these different types of solutions. But that is always a very difficult issue, and there's not really a very straightforward answer to this. It totally depends on the geometry, the severity of the displacements. But what I think is very important to keep in mind during these issues is that you should not allow for any gaps or any well, large gaps for these supports, because especially for these hammering effects, if the piping is not properly connected to the support, then the impact load will not be properly absorbed by the support, and you basically get a hammering of the pipe onto the support, and your support well, basically will deform over time if it is not very rigid. So it's definitely, you have to definitely keep in mind during any implementations of such that you allow for a very minimum amount of, of clearances between the pipe and the support. Okay, some final comments. So vibration due to two-phase flow. What we've covered are changes in density and then mainly the related impact forces. Often these are low frequency, so say around 10 Hertz, maybe even lower, but high amplitudes. Often these vibrations can be seen with the naked eye. Different approaches available, guidelines, flowcharts, vibration-based limits, and of course a mechanical response study can be performed. Typical engineering challenges, well, I've discussed some practical challenges. Obtaining data on the excitation mechanism, so these parameters that we've discussed, slug velocity, slug length, slug period, or the other parameters related to the relevant flow regime. A third challenge is to match the model with these measurements. So taking a quite conservative approach simply isn't enough. You have to take a realistic approach, such that if resonance takes place in the field, in reality, that you also find this in your model. And finally, there's always the tricky point that during this assessment you basically want to fix the entire system as much as possible to reduce all eigenmode shapes. But you have to keep in mind, especially for warmer systems, that the static solution still has to work out properly. Okay, thank you all for listening. I see I've taken at least 50 minutes in total. So before going to the questions, I want to take just 1 minute to show one slide about Dynaflow Research Group. So our engineering consulting firm focuses on 3 main pillars. So engineering, I think I've discussed a lot of that in the previous slides. Software, we release several software packages that we develop ourselves, amongst others. One is BOS Fluids, which is a 1D transient fluids calculation package for surge analysis, water hammer, and pressure fluctuations in piping systems. And the second one is IsoTracer. That is a new package that we released recently, on which I will discuss a little bit later on for those that are interested. And finally, one of the pillars is training, of which this webinar is a small part, and our training sessions form the core. Now, if you want to know more about these topics and the work that we do, as mentioned before, you can find the webinar page on LinkedIn. So the DRG webinar page, go to LinkedIn and search for DRG webinar or DRG webinar series. Please note that a lot of presentations are also available on YouTube, so search for the Dynaflow Research Group YouTube channel, and you can also find our LinkedIn company page. And if this is, well, too much work, you can always allow us to inform you whenever we have something, some interesting topics, by subscribing for our newsletters at dynaflow.com/news. All right, so before we go to the questions, I again have one question for you. And this is a small teaser regarding to the second part of this webinar, which is, do you ever model from or provide marking on isometrical drawings? We do this very often, and we ran into the situation where we found that it was too much work to do, well, a lot of work to do, and took a lot of time. So we basically tackled this problem by developing a new software tool, which is called IsoTracer. And I'm very curious about if you run into the same problem as well. So I just launched my second poll question. Hopefully you can take the time to answer this. Okay, so thank you very much. I will now close this poll question. Some final attendees answering. Yes, I will close it now and share it with you. Okay, so I think most of you answered yes, well, for those that answered yes, just stick around after the question session, and I will give a like 5-minute presentation demonstration of the IsoTracer software package. Okay. Well, basically this will come later on. Just continue quickly to the final slide. Yes. Okay, so thank you very much for listening. And I give the word back to Daniel.
Okay, thanks. Thank you, Luc, for this clear and informative presentation. I see we have received several interesting questions during the webinar. I will start with the first one. So, Luc, when you consider slugs, what's the density that you consider for the slug force? Do you consider the liquid density, or is there a mixed density?
Well, that is indeed a very relevant question. Basically, the best way to approach it, the most conservative way to approach it, is of course the liquid density. In some cases, our clients have done a very extensive, very detailed assessment of their flow regime. And they can provide some estimate of the density of slugs, whether a certain amount of bubbles is trapped in it. But I would just recommend use the liquid density. I mean, the eigenfrequencies should still be the same, but the displacements that you find will be more severe. So you're basically on the conservative side, maybe over designing some support for higher forces than they will see. But yeah, that's definitely the approach that I often use.
Okay, thank you, Luc. So better be safe than sorry and use the liquid density in your slug calculation. Another question by Matt is if there are any good criteria for velocity vibrations. I see you have already discussed some velocity charts by the VI, for example. Are these reliable? I think you already indicated something about that.
Yes, well, thank you for this question. Reliable as in, are they realistic? I would argue, well, not really, but they are definitely a very good estimate for the next action. So if your data points show to be on the safe side in these plots, in these vibration-based limits, then even though you have some vibrations, or even though this caused some worry, this is a strong indication that that it is not too bad, because I think you can imagine that the developers of these plots have to take into account many types of systems and all implement them in one graph. So you will definitely get a very conservative approach. And if you are, say, problematic in these plots, if your data points show very high values, yeah, then it is definitely a clear indication that you would have to check for example, potential fatigue failure. So that is the way I would interpret these values, and yeah, don't plot them if they are just below a certain line. Think that you're totally safe. They should be interpreted with a little bit of care, but take into account that they are conservative in most cases.
Okay, so they definitely give you a indication of what you can expect during your analysis. More questions regarding slug forces or slugs. How does the client or do you determine the length of the slug, or is it of any importance for your slug force?
Well, is it of importance? Yes, it is, because it determines the frequency of these impact loads on the elbows, and therefore basically the amount of response that your piping would give. How to determine them? That is a hard question. We had several projects in which we knew how much water, in that case, was collected in a steam line. So we had some information about how much volume was available, and this allows for some estimate of how long slugs can be, or how many you have, how many of them you can have. Yeah, that is difficult, and unless your customer, or unless you yourself are able to do a very detailed assessment of this flow regime, my approach would be to see which lengths, how they influence the stress amplitude that you calculate, and how this relates to the slug period, because the slug period is governing when it comes to whether you have forced or resonance type of excitation. But the slug length, the length that the force acts on an elbow is definitely of influence as well. But you would have to do some kind of parameter study to know more about it. Yeah.
Okay, thank you, Luc, for this clear, explanation. I'm just scrolling to the question, and I see a question from Benjamin. So when you model slug forces on a line, at how many elbows do you insert the forces? Do you insert them on every elbow, or just the more critical elbows?
Yeah, well, thank you very much for that question. Also, an important point when doing such analysis indeed. Well, what I often do is, in case of a failure, of course, I take several elbows around in the vicinity of the failed one, of the failed elbow or failed T, because you would have to get like all the force acting together to see if you excite a resonance mode. In case you're in a preliminary stage, what I often do is do one run with all of them, but then divide the line in several sections, of which I feel that the eigenmodes are excited. Eigenmodes are in that specific section are excited if I apply the forces to the elbows in that section. So just divide, take several of these elbows depending on lengths, of course, in your system, and see what happens there. But first step is to evaluate your eigenmode shapes, and if you have mode shapes that are only represented in a small section of your piping system, then you would only have to apply the forces in that section. If you have very long mode shapes, which include very long spans in your system, then you would have to take more bands into account.
Thank you, Luc. This is certainly something we can work with. Okay, we have a question from Antonio. He's discussing or asking about very high gas velocities, up to 0.5 or 0.7 times the sound velocity. Then when you have a little extra liquid quantity in your line, can this already produce slugs, or will you have different flow regimes?
Okay, well, thank you for that question. I think it is also quite a detailed question. I mean, for such high velocities, I mean, you could still check the plot that I've showed at the start, of course. You'd have to recalculate these velocities to the superficial gas velocity and the superficial liquid velocity. But nevertheless, these can provide some guideline, but for such high gas velocities, I can imagine that you will not find any very big slugs which act with a relatively low frequency as the ones that I have just discussed during this presentation. Because in the end, if you want to sustain these high gas velocities, you would also find a relatively high liquid velocity, I estimate. But yeah, you know, to such a detailed question, you'd have to have a detailed look, I think. But I would start at the flow plots that I just started, and also have a look at the books as I discussed them by Ove Bradland. Maybe he has some detailed information about these types of flow regimes.
Okay, thanks, Luc. And remember that the Ove Bradland books are free to download. Okay, so there's a question from Foria. She's concerned about the use of a snubber in your presentation. In one of your pictures, you use a snubber in the line to absorb the slug force. I'm not entirely sure whether that's actually your picture, but the question is why you would use a snubber in the lateral direction while the slug flow, of course, the slug force will be in the axial direction. Or related to this, in order to be able to accommodate the high slug forces, would it be better to use a support in the axial direction, or?
Well, that's a very valid observation, and that is also what I try to explain at the moment that I had this slide on the screen. So I totally agree with you. I mean, the snubber as is installed on the slide that I'm showing at this moment is totally ineffective to absorb impact loads. So maybe, you know, in the past some of the engineers have observed vibrations in the lateral direction and therefore choose to, as a first approach, just to install these snubbers and see what happened. But this is definitely not a recommendation that we did, because yeah, you'd have to apply it in the axial direction, and you'd also have to apply a much more rigid structural attachment to totally eliminate the vibrations.
All right. Yes, thank you. So I think we may have time for one more question. Okay. So these questions are a bit related to the dynamic analysis in CSAR2 by Bob Zimmerman. So when you have your your velocity measurements translated to a frequency versus a velocity root mean square, how do you input this data in CSAR2?
Yeah, that's a very good question. Let me just take a moment to find a slide which I can use for this. So if we look to the piping segment on your right, on the right side of the slide, basically what we see is the directions of the forces exerted by the slug loads. And for like more easy configurations like this one, the first approach would be to just apply these forces on the different nodes. And this is one of the options you can do in the dynamic modular of CSAR. And if you apply these forces as a time history to these nodes, then you can really see if your input allows for excitations of these eigenmodes. And for this system, it is rather easy. You just have to calculate the slug velocity, or at least you know the slug velocity at that time, and you have to take the time delay into account and then apply them and see if it matches the observations in the field, for example. But if you have much more complex geometries with, for example, T's and multiple branches, which are all fluctuating or vibrating, vibrating to some extent, then it becomes more difficult to use the forces, to apply the forces to your model. And one of the solutions that you can use is just to implement forced displacements. Now, of course, it's very important if you do so to see if you actually, if your system actually shows the eigenmodes that your measurement data shows. Because if it doesn't and you're using these forced displacements, then your response will be quite different from the reality. But that is sometimes the only way to move forward, because if you use forces on a very complex geometry, then you're often not able to represent the right timing, for example, or the right mode shapes in the response of your system. So I would start with implementing the forces node by node in your system, and see if you get a match with your measured data, and otherwise implementing the displacements that you measured directly on the piping might be a solution.
Okay, thank you. It seems that I misinterpreted this question a little bit. It's more about whether Caesar2 can perform the fast Fourier transform, or do you do this outside Caesar and then use the result from the fast Fourier transform to input the loads in Caesar?
Well, no, the first thing that you would have to do is just think about the force value, the impact load, and think about the time difference that it takes for this force to act on the different elbows, and then you apply these forces directly on the piping. So no Fourier transform, fast Fourier transform is necessary with those steps. However, if you choose to relate it to measurements, then you would have to transpose your measurements, accelerometric measurements, to usable data, and that definitely involves a fast Fourier transform that you would have to do yourself. And by doing this fast Fourier transform, you can also find the displacement as a function of frequency or as a function of time, and those values are the alternative that I explained before, that you can use on the piping as well. So then you have certain displacement of a certain amount of millimeters or inches at a certain location with a certain frequency, and those you can apply to the different points in your system and see how the response of your system, how your system responds. But I'm not familiar with Caesar2 actually doing the fast Fourier transform for you.
Okay, thanks, Luc. I think I recall the same. So let's wrap up this question session, and keep in mind that all questions asked during this webinar will be posted on our LinkedIn page. So for future reference, or if you want to check the answers again, you can always check the LinkedIn page. And now for the people that are interested in, well, there you see it, 50% faster modeling, can stay tuned.
Okay, well, thank you, Daniel. I will now continue with the final part of this webinar, which will take about 5 minutes. It will just be a brief demonstration of the IsoTracer software package that we released. I already pitched obviously the problem that we ran into, so that it takes a lot of time to go from the isometric to the model, a lot of modeling time, and then also you'd have to do the marking by hand. And we felt that this, could all be avoided if we would do it in a more effective manner, and that's why we thought about this and developed IsoTracer. And we found that if you use IsoTracer, well, even our more experienced Caesar modelers, so to say, once they get acquainted with IsoTracer, which takes about like 1 to 2 hours, even they can reach a much faster modeling time, a much shorter modeling time. So there's definitely a very strong reduction. And I will give a brief demonstration of the software in a minute. Other added values, of course, are the automatic markings done by computer instead of by hand. You can export your model from the IsoTracer package directly into your stress software package. Of course, that is one of the main functions. You have an interactive 3D model, and I myself find that very convenient if you work with a lot of isometrics. So say you have a software system with 80 isometrics, and then this interactive 3D model allows you to click anywhere in the system, and the software automatically takes the right node and the right location of the right drawing. So you immediately have the information available. Instead of going through all these isometric drawings and all these stacks of paper. And superior quality control, you can manage your isometrics, export them to very neat PDFs, neatly marked as well. The quality of your markings is also, well, it's all done digitally, so very neat, I would say. Okay, so finishing this, let's just show you what the IsoTracer software would look like. So what I have here is a prefab example that I have made. Basically, the IsoTracer software package consists of one section in which the drawings are present, one section in which the drawing is visualized, and one section in which your model is visualized. Now this module is 3D and interactive, as I explained before. And if I go to the markup tab, we can see that all the piping nodes are provided here. These can all be changed, but I will demonstrate that simply by starting a new project. Maybe I have it. Yes, there it is. So here I have two isometrical drawings. This is number 1 and this is number 2. And now I will just simply do a brief modeling of this. So I start tracing. I just press on the starting node, choose a node number, say 1000. Okay. So now we see that I have a red line which follows me. And I can use it. Well, first let's just move this marking. And I can now click on the next node location that I want. Now the length, I have to implement that every time that I click, but since that is the only feature that I have to implement, the modeling goes very quickly. Also, in the first time you model a pipe section, you'd have to do the diameter and thickness. So let's just choose some values here, arbitrary values. Now I think one of the neat parts of this software is when I click again, I have to implement the length as I mentioned, but you see that the direction that the IsoTracer software package selects for this pipe segment is the correct direction. And that is caused by the fact that we have this coordinate system that we can change the directions of this coordinate system if necessary. But for now, for this isometric, they are all properly defined, as you can see. Yeah. And it uses these coordinate definitions to provide the modeling. So I just want to continue, extend. So this one here. And I think you can now clearly see that if I just click through my model and implement the length values, that you can really quickly build your model and do all the markings at the same time. Now, one of the other neat features is that if I come to the end of a isometric, I want to start on the next, I just simply select the next one and click on the starting point. It then gives the name of the isometric, the connected isometric. It again gives the node numbers, and the models are just simply connected, and I can just simply continue. So I think that briefly shows you the value of this package. If I just continue for a little while more. Even if we have angled sections, the interpretation is very good and it takes the right direction. So for this section in the isometrical drawing, you see that there are several rigid elements, so valves, and you can just include them by, first include them. And you can select, instead of pipe, you can select rigid and include the weight of these rigids. So by doing so, let's include this one as well. And then a pipe section again. Yep. Okay, so by doing so, we see that the rigids are already included in the model. By clicking to the relevant location, the software automatically takes the relevant isometric drawing. So that was a quick demonstration of this line segment. You can also do T's and branches, of course. It's all fine-tuned for easy use. So let's say 2000 for this branch. And we simply start clicking. We have to implement the length. That's the only value in most cases have to provide. That's a typo from my end. Okay, so I think it's clear that all these steps, if you want to go quickly through these isometrics, it really allows you just to click through these pipelines and build your model. An additional feature that you can provide, well, one of the many features that you can provide are supports. So if you want to add a new support, say for example a rest support, so Y support in the positive direction, let's use a friction coefficient of 0.3. We can simply select the node and we see that the support is automatically generated. All this information that is built up in this file can be opened in, for example, Caesar as well. So if I just go to Caesar, 1 minute please. So if I go to Caesar, this is the model that I started my presentation with. So the full model. So you see, I took a little bit more time to define all the support types, all the elements, all the rigids. I even defined some markings, some textual markings, which is also possible in IsoTracer. So these are really a set of isometrical drawings that can be included in reporting. We see the entire system, the 3D model as well, including all the supporting directions. And this one was exported to Caesar to find the following. So basically you export a file which you can open in Caesar, and you then find your model being available here, including the right weights of your rigids, including the right dimensions, thickness, diameters. And basically you just have to define your material, and then you can start analyzing, and of course your load conditions. And the next versions of IsoTracer will probably include more of these features, so that you can even define the material or more of these features in the software package IsoTracer. But for now, it is a really neat tool to go from an isometrical drawing to a stress model in one step. And by doing so, you eliminate the step where you have to provide markings on these drawings by hand, and I think that is also one very big time saver. So a lot of more features available. The software, for example, automatically selects if something is a band or not. You can also toggle that on or off. You have several something that we call chains in these models. So if you start one modeling direction, one pipe segment, and then you define a second, for example a branch, then that is defined as a separate chain. And you can see those in the chain monitor, because these node numbers are not allowed to overlap, of course, because then your stress software package would interpret that as the same node. So we have a lot of these features. I think it's really neat to just have a look at this. This software package can be downloaded from isotracer.com, and you can just download a free evaluation version. So if you just go to isotracer.com, you can have a look at some video demonstrations such as this one, several models that we've built, and some information, of course, about pricing, about features, about support. But you know, for now, I would say just download the evaluation version, and you can already input your isometrics and just start modeling, see you know, get acquainted with it and see how it feels, and I think you will soon enough conclude that it really helps to provide this quick modeling and marking with very good quality. Okay, so that concludes my brief demonstration of IsoTracer. If there are any additional questions or remarks that you would like to make, feel free to contact us. Just go to the last slide. You can always contact us directly on webinar@dynaflow.com, but you can always also contact us on the webinar LinkedIn page. And if you want to have more information regarding the IsoTracer package, I would recommend you to have a look at the website and follow the contact information that is provided there. Of course, you can also email it to webinar@dynaflow.com, and we will forward it to our software engineers. Okay, so that concludes my entire story. Thank you very much for joining us today, and have a great day. See you next time at Dynaflow Research Group webinars.